let's focus now on macro scale, on the overall structure of the food web. This is first described by what we call topological properties. Those are very summary metrics that tell us about general properties of the food webs without going too much into the details of how interactions among species are structured, what are the classic patterns of interactions. No, these kind of summary topological properties tell us a very broad and general descriptions, which is nevertheless important at the moment we are going to compare across systems. Those are S, the number of species, which is the number of nodes, how many species are taking part into these food webs, and L, the number of interactions, the number of links, how many feeding interactions are taking place among those species. And from these two numbers we can already calculate the mean number of interactions per species, which is L divided by S. You can imagine that this mean number can tell us something about the complexity, even though it doesn't go into the details of how interactions are structured. And likewise, a similar property is what we call connectance. This is indicated by the symbol C and is calculated as L divided by S to the power of 2. And this indicates the proportion of possible realized interactions. The complexity explained as the number of interactions that are occurring over the potential, the ideal number that is possible to realize given this set of species. If the food web doesn't consider cannibalism or intra-guild predation, then the equation shall be corrected as in its form on the right. These four basic properties are already telling us some general patterns in food webs. For instance, the number of species ranges between 10 to 100, the number of interactions between 10 to thousands, and the connectance is usually around 0.1 with a range between 0.03 to 0.3. So we can already see that by just describing food webs with this simple connectance, we can already tell a lot about the complexity of the food webs. Other basic topological descriptors are the proportion of basal taxa, the so-called autotrophs. Those are the species that don't consume, don't prey other species, and in general they are the photosynthetic organisms that convert the inorganic matter into organic biomass. Those are usually depicted at the base, at the bottom of the food web. Then we can also look at the intermediate species, the proportion of consumers and resources taxa. We already know that the same species, like the anchovy, can be at the same time a consumer and a resource. And this can tell us about how the flow, the transfer of matter and energy is going to move from basal to top. At the top, indeed, we have these taxa with no consumers, and its proportion tells us about the sustainability of the food webs. For instance, if we consider that there is always a loss in efficiency across the food web, then the number of taxa that a food web can support is quite constrained. The higher the number of top predators, of top species, the more the energy is required. So at constant energy, reducing the proportion of taxa with no consumers is going to increase the efficiency and the energy demand of the system. Finally, we can also look at the average trophic level position. The trophic level, as it is defined as the rank along with a taxa is located. For instance, the bacteria are trophic level 1, likewise the phytoplankton, those because they are basal taxa with no praise. A trophic level 2 is going to be a species that is feeding on a taxa with trophic level 1, and so on and so forth. This average trophic level position is also an indicator of food web complexity and how much the food web is moving energy and matter. A food web with a very low average trophic level position is probably resulting from a degraded, over-harvested, overfished community. Instead, a community with a relatively high mean trophic level, it's indicator of a complex and structured and somehow stable food web. We can also look at other topological properties that involve the food chain, the connections among different species. This is quite relevant because, as we saw before, food chain is a building block, is a motif, is this recurring pattern that constitutes the basic structure of food webs and has important implications for its dynamic and stability. In this way, we can calculate the mean food chain length. For instance, if we take all the species in the food web, we can calculate the number of links necessary to move from one species to the other. In this case, if we consider the phytoplankton and the sharks, we can see that from going to this basal group, to this top predator taxa, we need 1, 2, 3, 4, and 5 links. So in this case, this food chain between phytoplankton and sharks is equal to 5. We can repeat the same exercise for all the pair of species and then calculate a mean food chain length. As every kind of average property, it is important because it can synthesize, can tell us already something, it can estimate a population trend, but it can also mask the variance, the heterogeneity in the food web. For this reason, we can also calculate the standard deviation of the mean food chain length. This is going to be more meaningful in highly complex food webs because the heterogeneity in species connection, and so the food chain length is going to be quite high, so it's important to include a measure of variance. What we can also finally calculate is just the number of food chains, and in particular the log number of food chains. This is important when we indeed want to then again estimate and compare complexity and then henceforth infer the stability of a food web. We mentioned previously the path length when we were talking about the centrality of a species, and in particularly the betweenness centrality. We mentioned this path length, which is basically the mean shortest set of links between species pairs. So in this case, if we want to move from phytoplankton to the birds, those two species are not directly connected, but we want to understand how many species are necessary to connect those two. And in this case, quite surprisingly, it's enough just one species. So in this case, with two trophic interactions between phytoplankton and birds, we can connect these two remotely distant species. It was discovered that actually food webs have a quite short path length. Indeed, it's possible, on average, to link all species pair within two links. Another important average topological property is the so-called clustering coefficient. If we take a pair of species, like in this case the anchovy and the plicard, we can calculate the probability that these two taxa that are not linked to each other are going to share the same taxon. And this indicates us the probability of cascading effect, of spreading these indirect effects, because as we saw before, two species can indirectly compete or facilitate each other. The higher the clustering coefficient, that is, the higher the probability that two species not directly linked are linked through a third one, the higher the possibility of having cascading effect, and this is going to impact as well the robustness of the food web. We can then look at full-scale properties. A very important properties that was imported in food webs from statistical mechanics, it is the so-called degree distribution. We remember that the degree is the number of links per species, which is the number of predators and prey of species and of each species. So if we repeat this exercise for the whole food web, then we can plot the distribution of these links, and we can derive a probability distribution for the species degree, for the number of interactions. In this case, we will take each species, as depicted here on the right, and calculate the number of interactions for each species. Then, on a Cartesian plane, we can plot on the x-axis the number of links, the number of interactions, which is the degree of the species, and on the y-axis the number of species that have this particular degree. It's interesting that random networks, as they are depicted on the left here, with this distribution that resembles a Poissonian, or with increasing the number of species to a very high number, as it is done in statistical mechanics, to a Gaussian. This represents a classic distribution for certain random networks. However, real-world empirical food webs that we observe in nature and we want to understand are not characterized by this kind of Poissonian distribution. Instead, as it is depicted on the right, they have what is called a zip or a power law distribution. In this case, we can see that there are very many species with a low number of links. Those are at the left of the plot with a small number of links, and they are very abundant, they are very common. On the other hand, with this decay, with this exponential decay, we have at the other side of the gradient very few species that instead have a high number of links. So this resembles as this power law distribution and the famous expression rich get richer, where in the case of food webs, again, we have very few species that are feeding and are fed on many species. Those are few species with many links, and then there are many species with very few links. Then we can also look at structural patterns of interaction, and we can dig inside the architecture of these interactions, how particularly species are arranged and interacting with each other. This is mainly characterized by what is called modularity. So let's first introduce what a module is. A module is a compartment. It's a set of species that are more strongly connected among each other than with species belonging to other sets. This is represented here in this cartoon at the bottom left, where we can see 3 modules. Each module is characterized by a certain number of species that are really tied together. And among those, there are few species that have links with species in other modules. This is, for instance, in our Benguela food web, is depicted here on the right with these 3 different colors. We have, for instance, those basal species that represent a module where there are lots of connections among themselves, and few species have connections to species in other modules, like in this case the intermediate top predators. So modularity is then defined as the degree to which food webs are decoupled in densely connected modules. The higher the modularity, the higher the organization of the food web in these compartments. The more there are species with have many links within their neighbors, and few species with few links to other modules that are connecting and keeping together these food webs, because we remember that on average we can move from any pair of species just within 2. So this modularity is very important because on one hand it creates these compartments where species are somehow interacting in their small subset, but on the other hand it keeps cohesive the network. Indeed, we will see that modularity is very important for increasing the stability and the persistence of species, and particularly the robustness of the food web. Because we can imagine that a perturbation that is going to affect a module maybe can be dumped within the module without affecting the food web. These structural patterns has been found to be very common also in other type of ecological networks. So, wrapping up this part, we have learned that food webs have certain recurrent properties. There are these kind of quote-unquote universal laws. Usually they have uh, 10 to the power of 2 species and links, a connectance within a range between 0.5 and 0.25, 0.3. They are highly heterogeneous. They are not distributed randomly. This is because there are specialist species, species that feed on a small range of prey, and generalists, those omnivores, those top predators that feed on a broad set of prey. But food webs, they are also closely, fully connected through many different food chains. There are many paths that can link two remote species. As we saw before, just from the phytoplankton to the birds, it's enough having one other species. With two links, we will move from the bottom to the top of the food webs, and even from the ocean to the air. And this indicates us also the importance of these pervasive direct and indirect effects. We learn that there are those motifs that are overrepresented that can lead to spreading the cascading effects, and this is going to impact the dynamic of the food web and its robustness. Finally, we learn that there are sets of weakly and strongly connected species. In particular, in these modules, there are species that interact strongly with each other, and few species make those bridges with other modules. This modularity also is a recurrent property that is going to affect the stability of the food web.